Okay, um, so this is lecture 11, which is on images. I have posted on the course website, um, whoops, refresh, Project 2G, and it is a little involved, and so this information will all be about how to do 2G. Um, I guess the way it's ended up, there's some starter code, which I've heard from you all, you find starter code confusing. Um, I just was really actually trying to protect you guys that there's spots where things can go wrong, and so I've added like some support here and there, and then the more and more support I've added, the longer the code's gotten. But I will in this video spend time talking about what's in the starter code. So let's talk about images first before we start to talk about the starter code. And so here's a little background on images. So an image is a two-dimensional array of pixels. And so what is a pixel? A pixel is I'm just going to read this, minute area of illumination on a display screen, one of many from which an image is composed. That sounds like a circular definition. So let me bring one of these up. Here's the output of your project. And if I zoom in, I think in the nostril, we can see individual pixels. So this is one pixel with one color. And of course, this image is made up of many, many pixels. So the way computers do pixels, to me, is a bit odd. When I was a kid, I learned that there were three primary colors, red, blue, and yellow. And I did great experimenting in preschool of taking Play-Doh of many colors and mixing them together and seeing what would happen. And so when I was a kid, if I mixed yellow and red, I would get orange. If I mixed yellow and blue, I would get green. And if I mixed red and blue, I would get purple. Computers work differently. So computers, instead of using red, blue, and yellow, they use red, green, and blue, specifically in that order. And so you'll see this RGB used in a lot of abbreviations, and we'll be following the RGB format. And so you can think about the amount of color for each of these three colors. Sometimes they're referred to as channels. What's in the red channel, what's in the green channel, what's in the blue channel, as ranging from 0, meaning there's none of it, to 1, which means there's as much as you can have. And so and so here are some examples. If there is all the red you can have and all the green you can have and no blue, on a computer that makes yellow. That weirds my brain out. It's not what I learned when I played with Play-Doh. If you have all red and no green and all blue, that makes purple. That fits my preschool Play-Doh experience. And if you have all red, no red and all green and all blue, that makes cyan, which is kind of like a light blue. I don't know, it's a mix of blue and green, I guess. And then if you have all the colors, red, blue, and green, you get white. That kind of makes sense to me because white is the presence of all colors. But of course, in my Play-Doh experiences, it would have been brown, I think. And if you've got no red, this is not on the slide, but if it's 0%, 0%, 0%, then you would get black. So all of this is thinking about three, again, I'm going to use the word channels, three color channels. And what if you have some percentage in each of the channels, what total color do you get in the combination? It turns out that there's a trick that computers use. And so the trick is the following, that we can think about the colors from being 0 to 1, but then how much resolution is needed. So do we need like a floating point value for every color? A float from 0 to 1 for red and green and blue. As we've been learning, a float is 4 bytes. Maybe that's not enough resolution. Maybe we need 8 bytes. So that'd be a double. And so we'd have 8 bytes for red, 8 bytes for green, 8 bytes for blue. That would be 24 bytes. And so the question is, how many bits do we need to represent colors? And so to answer that question, I'm going to say, well, if it's, it says 32 bits, so I'm going to say, can your eye tell the difference between 8 bits and 32 bits? Aha, so this would be, 8 bits would be 1 byte, and 32 bits would be 4 bytes. So in C, when you have 8 bits, that's represented with the unsigned car type. And so I should probably write that in my notes, in my slides. So I'll modify these slides to represent that. So if you have 8 bits, that's a byte, and people treat the unsigned car as 1 byte. Again, 32 bits would be a float. So can your eye tell the difference between them? The answer is no. Your eye cannot tell the difference between 8 bits and 32 bits. The human eye can distinguish about 10 million colors. If you have 8 bits for red, 8 bits for green, and 8 bits for blue, that's a total of 24 bits. 24 bits would allow you to represent 16 million colors. So interestingly, at least interestingly to me, some of the 10 million colors that we can differentiate, can distinguish, the computer can't make. Obviously, there's colors the computer can make that we can't see, because it can make at least 6 million more colors than we can see. But it turns out we have some that we can see that it can't make, but it's close. So instead of going from 0 to 1, then, colors are actually represented from 0 to 255. Let me just write this in my notes. That 1 byte is the same as an unsigned car in C, and the unsigned car has values that go from 0 to 255. And because 8 bits, 2 to the 8th is 256, and so the values are from 0 to 255. So then red would be 255, 0, 0. In the previous slide, we had talked about 0% and 100%. Now we're saying the value 255 is red, the value green, or the color green would have an RGB value of red 0, green 255, and blue 0, and blue would be 0, 255, 255. And so this is how colors are stored, and in fact I haven't put it in the prompt, but I'm just going to write it right here. You'll have to type it yourself, but if you look at proj2g.c, what this means is I'm going to have in my pixel struct, I'm going to put unsigned car RGB. Or, if you'd prefer, you can say unsigned car R, and then have 1 per line. That's probably fits better what we've seen so far, and it's more typing, but so what? But they're both the same. And so this is what we're looking for the pixel struct, is you have an unsigned car for the red channel, the green channel, and the blue channel. Okay, so you'll have to type that in, because this is just my copy of the prompt. So then, how do you organize a struct for an image? An image is actually a 3-dimensional array. So the first 2 dimensions are pretty obvious. There's a width and there's a height, and so those are 2 dimensions. The third dimension is just the red, green, and blue channels. So it's a 3D array that it's width, height, and then red, green, blue. And so then how do we represent this 3D array? Well, I've made some decisions for you in this project, and there's actually multiple right ways to do it. When I've taught the 330 class in the past, I've allowed people to do it however they want, but this time I just thought it'd be easier to say this is how I intend for you to do it. So the first decision is whether you'd like to have a struct, a pixel struct, which is RGB, and you see I have an asterisk here. The asterisk means this is my intended decision for you. But another thing to do would just be have 3 unsigned characters, and so if I wanted to have, for example, an image that was 1,000 in width and 1,000 in height, well, 1,000 times 1,000 is 1,000,000, and another way to do it, so one way to do it is to allocate 1,000,000 pixels. That's what I'm advocating for. Another way to do it is to allocate 3 million unsigned characters, and I'm not advocating for that, but that would be because there's no asterisk there. And if you have 3 million unsigned characters, then you'd have to do even more indexing. And with this choice, you get to do less indexing because it's just 1 million pixels. The other idea is how to store the pixels. And so one way to do this is to do pointers to pointers. And so you'd make for every row, you'd have a pointer, and then that pointer would point to all the data along that row. And so then you can do nice two-dimensional indexing. So the upside of that is you can say, for, I was going to do it with my hands, but since my hands aren't very clear, I can type. Here we go. So if you do this pointer per row, that means that you're going to have your data like this. And so we have pointers to pointers. No one gets too excited about pointers, but it has this really nice property that you can do this. And so then the code that you write is really clear after you've figured out the pointers to pointers bit. I am not advocating for that because there's no asterisks there. Instead, I'm advocating for choice number 2, which is to just index it. So let me do a quick example. Here's an image. And so this image has 4 columns and 3 rows. And so I think most people would call this a 4x3 image, but sometimes I get myself confused on this stuff, and sometimes I'm dyslexic, and maybe people would call it a 3x4 image, but I don't think so. Whoops, that was too much. Escape, undo, redo. Okay, and so we have here a 4x3 image, and I've labeled every pixel as having its own. I've given every pixel its own label, and so in this case we have a 4x3 image, so we're going to have a total of 12 pixels. And so when we do our mallocs, we're going to do something like this, where we're going to have some pointer we want to initialize, called like maybe colors. And we'll say equals, malloc size of pixel times 12 or whatever. And so then we've got 12 pixels, and they'll actually be stored as A, B, C, D, E, F, G, H, I, J, K, L. But of course, an image is really a two-dimensional array. And so even though we're storing it as a one-dimensional array like this, we need to have some way to still conceptually think of it as a two-dimensional array. And so there's a formula for this, and the formula is that you take the row number and you multiply it by the width of the image, and you add the column index. I said row number, but I probably should have said row index. So I could write this, if I'm going to write it in column row form, then I could write this as 0, 0, 1, 0, 2, 0, 3, 0. And then, I can look at these and say that A go at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then if I were to go to G, G is at a column of 2 and a row of 1. And so it would be 1 times 4, which is the width, plus 2. And that's equal to 6. And if I look right here, G is at 6. So there's this formula here that when you want to deal with again, what is the index of CR? Well, the answer is this, row times width plus C. So as you're manipulating images, you'll want to get the pixel at CR, and you would then use this formula. And I actually have a helper function for you. And so, for example, if you have, equals something and a row equals something, then you could do something where you say index equals get pixel index of column row, and you probably have to pass in the width too, like a width of 4 and a height of 3 or something. And then once you've done that, you can go to colors of index, and you can talk about its R value and its G value and its B value. And so in the prompt, one of the operations you have to do is set certain pixels equal to yellow, and yellow is when red is 255 and green is 255 and blue is 0. So then the idea is you're going to be often thinking in terms of columns and rows, and there's a way to get from a column and row a formula to convert to an index, and once you have that index, you can go to your colors array and then access the individual channels, the red, green, and blue channels. Okay, good. I have done this video once before. I'm refilming it for this 212 class, and so far I think I've done better than I did before, because the previous video had some mistakes and then I had to post a lot of corrections. So far so good, I think, although maybe you'll tell me I've done it wrong. Okay, so there's a lot of image file formats out there, and here are things you've probably heard of: PNG, GIF or GIF, TIFF, JPEG, and one you probably haven't heard of, which is PNM. And we're actually going to use PNM in this project because PNM is far and away the simplest to read and write. So here's a slide that says the same thing. Most image formats are hard to read and write, and people will then use libraries to encapsulate the reading and writing, but these libraries actually create all sorts of problems for us. Also because the formats are actually pretty complicated, and they do things like encode the date that you wrote the image at, and so then it makes differencing very hard, so we can't actually tell if we got the same thing. So instead we're going to use PNM. PNM is part of this so-called NetPBM library. Again, the key advantage is it's very easy to read and write. The key disadvantage is it's not supported by many tools. Although, in the virtual machine, you can install a package, and here's my installation command right here, sudo pacman sy imagemagick, and then if you do that, then you can use a command called display, and here I've called display on the image I've downloaded, and you can see the image. Does it make it smaller? Is there a way to make it smaller? Well, I'll have to look that up. I actually may make the images smaller after I film this. And so that's how you can look at the images in the VirtualBox. If you have a Mac, I actually have it set up on my Mac to look at PNMs, but it involves installing software. For what it's worth, several of you have learned that I actually have not been using the VirtualBox. It's been something I've asked our TAs to support, and but I've been trying to use it and get more familiar with it and kind of feel your pain, because I've been hearing from people there is pain. I get it, and so I think that if you have a Windows box, you're going to need to continue to use the VirtualBox. If you have a Mac, you actually can use the terminal and code things on your Mac and then just copy it over to the VirtualBox when you're done. That's certainly fine by me. My only interest in you using the VirtualBox is I'd like you to validate your solutions work there. Okay, so how does the PNM format work? So I've downloaded several of these, and so I'm just going to do a VI on this. So here's a VI on the input file, 2G-PNM. And again, I think I'm going to change this because I'm going to make the images smaller. So these numbers right here will change. And so this is just a format. This is this is how they've decided to lay out the data. The way they're laying it out is they have something saying that this is the P6 version of the file. Certainly, you will be reading one file for this project, and it's P6, so you can safely ignore that. And then a width and a height. And then this is another, to us, useless value. It says what the maximum value is. in case it has a resolution higher than 8 bits. And for us, it never will. It's 255, and we can throw it out. And then after these 3 lines, well, we get a bunch of weird-looking stuff. And so that's actually the binary data. And so if you read P6, 1786, 1344, and 255, and this new line right here, then the file position indicator will actually be pointing at the binary data. And the way the binary data is stored out is like this. So it's P6, 1786, 1344, 255, and of course new lines. And then it will be for pixel 0, what's the red value? For pixel 0, what's the blue value? For pixel 0, what's the green value? And for pixel 1, what's the red value? Pixel 2, what's pixel 1, what's the red, green, blue, what's the green value? What's the blue value? And so on and so on, all the way to the last pixel, red value, green value, blue value. And so once you've read the P6, 1786, 1344, 255, and the new line, you can just start reading the binary data in as unsigned characters, because that's how C represents bytes. And I'll show you in the starter code. So here's a struct for pixel. We already said this should be unsigned car RGB. Here's an image. The image is going to need to have a width, a height, and some sort of pointer to an array of pixel data that you'll be indexing, in this way, where you'll store it as a one-dimensional array, but then you'll need to index it with this sort of magic right here. And so then if we look at the starter code, here's a read image. And by the way, in every function, I have put in a print statement saying that you've started the function and then you're ending the function. And I've put in some lines here, and I actually think I have a slide on these lines. So let me go to the slide. There is a partner to printf called scanf, and this scans from a string. So it is the exact opposite, or not exact opposite. It's the mirror image of printf. So if I were to say scanf and I were to give it a string, and then I could say, well, I would like you to scan from this string. So if the string has P6, new line, 1000, new line, 255, and I say, well, this is the syntax. There's going to be something I don't know what it is, and then a slash, and and then a new line, and then something that's an integer, and a space, and another integer, and a new line, and another integer, and a new line. And you say, well, put the string in magic num, put the integer in width, and of course we have to give it an address so it can put it in the location the address points it to, put the next integer in this int, and the next integer in this int. Then if you call this function right here on a string that looks like this, then it would place P6 into magic num, it would place 1000 into width, it would place another 1000 into height, and it would place 255 into max val. So this is actually pretty magical in terms of reading in the image, the header part, the ASCII part of the image. And you can see it's right in there, except for instead of using scanf, it's using fscanf because it's reading from a file. And so you can just uncomment these lines, and if you're doing, see here, I'm assuming that you have a file struct, file star, called fn, where fn is the name of the input file. And if you uncomment these lines, at the end of it, you'll have the width and the height, and you'll have parsed out, all the stuff at the beginning of the file, P6, 1786, 1344, and 255. And then the file position indicator will be pointing directly at the pixel data, and you can just start doing some freads. So hopefully this will make the task of reading an image in much easier. Let's see, so I guess the rest of this is, I have to update this. On Project 2G, the prompt is posted as of right now. I've really struggled with when to make this do, and so this is actually no longer true. It's now due on Saturday, November 3rd. Um, this is a toughie. This project is about 50 lines of code, so that's more than the other projects, and it's 50 hard lines of code. And so, this class has been tough so far, but it's been tough because you've been developing all of the skills, how to use VI, how to do debugging, etc. And so now we're assuming that you've got that foundation in place and that you're ready to do some tougher tasks. And this is a tougher task. I wanted it due on Thursday because I wanted to support all of you, and I'm leaving on Friday, and I didn't want it to be that I give you this tough project and then I leave. So actually, I would really like you all to try to finish by Thursday, and I'm actually going to offer extra office hours while I'm here, which is in the form of Tuesday after class. When the lecture's over, I'm just not going to leave, and I'm going to stay there and answer whatever questions you have. And I actually think it's critical that all of you get started and try on the project and bring questions Tuesday after class for that office hour. And hopefully I can get you on track. And Thursday we'll do it again. And so I would like it actually be due Thursday, because I think if people scramble and they're coming to office hours, they could get done on Thursday. But at the same time, I think this is one of our hardest projects so far, and I just didn't think it was fair to give you 5 days. And so I'm trying to do my part by offering extra office hours this week, and I implore you to start early on this one. If you wait and say, oh, well, Hank's giving me till Saturday, and I'm just not going to start looking till Friday night, I think you're going to have a really frustrating time, and it's not going to be possible for us to support you. So, I part of the reason that I'm giving you so much time is because I want you to start right now, and to be coming with your questions to office hours. Again, I have one on Monday. I'll have another half hour on Tuesday after lecture, and I'll do some more on Thursday. Okay, so that's it for the slides. And before I sign off, I'll just look at some more of the starter code. So if we go down to main, so main calls verify input first, and this is a function that does really nothing. You don't have to look at verify input. What it does is it makes sure that the images you're supposed to open are there, because I just didn't want people to be running into failures because they tried to do an fopen and the image wasn't there, and fn returned null, and then they were getting crashes. So right away, if it cannot find 2G input.pnm, it will let you know. And also, if it can't write 2G, if there's some sort of pseudo problem where you can't output a file, it'll let you know that too. There's 3 images, so source image, yellow diagonal, and left right. And so it will read an image, and then it will immediately write the image. And so if you read an image and immediately write it, it should create the exact same thing that you just read in. And so, I really encourage you guys, beg you guys to be doing this in small chunks. And so you should write a reader and make sure it compiles, and add some print statements. So here in your read function, you'd implement this, you'd add some print statements to make sure you got the widths right and the heights right, and that, at the end that, that you've actually malloc something that's a real pointer. And just do some sanity checks that you've done something that seems reasonable, and then you'd implement this write image. By the way, you see here there's a hint that says use fprintf. This fprintf would not be the standard error; it'd be to the file that you'd open up, the fout file star fout equals fopen of file name with write, and then you'd be doing an fprintf on that fout. And just write those 2, and then run it, and see if the 2 are the same. And you can see the rest of the stuff, the other 2 functions, are actually commented out with macros, so they're both if zeroed. Now I tried to put together what I think is a nice script, and this script is doing some checking. Do you have the input image? And then it compiles and it will run. And if your program didn't complete, it will stop. And if it did complete, it actually tries to do some differencing for you and give you some tips about what might be going wrong. And so you can see here, it will run and we'll say, well, so if you look at read image, and then it will do a write image, and it will call the output of read. And so then the very first thing it will check is it will check to see whether the input, the one I give you, is the same as the output of read, the one that you would be implementing. And if they're the same, it says they're the same, good. And if not, it calls this function diff files. And so diff files, the first thing it will do is it will look at the headers. And so by the headers, I mean something like this, where it will look at these three lines and make sure they're the same. And if they are, then the next thing it will do is it will look at the file sizes. So we'll do an ls-l and make sure that the file size, for example, of 2G input has this many bytes, and the output of read has also the correct number of bytes. And then if you got the headers right and the number of bytes is the right, then it says, hey, you should probably look at the images, because it's actually, you've written a file probably correctly, but the pixel data is different, so you need to look at the pixels. And then it will do that with the output of read, and you don't need to uncomment. You don't need to uncomment these if zeros. Just run it. Just implement read image and write image, and then run check 2G. And you see, then it will run it, and it'll say, oh, they match, good. And the next thing it'll say was, oh, I couldn't find a yellow diagonal. So it says, you have successfully created output of read. The next step is to create yellow diagonal. Go change that if macro in main. And then it will do the same thing over again, where it will compare your yellow diagonal with the solution. So by the way, you need to be going to the website. And under 2G, you see here's the starter code, here's my script, and then for all of them, there's going to be a PNM file, which is the easy one to manipulate, and a PNG. You don't need to download the PNGs. I just put it there so you can just click and look and see what they look like. So the yellow diagonal one will make something with a yellow diagonal that goes through it. And then the last one, the left-right combine, will make something where there's the two are together, the original input and the yellow diagonal are combined left to right. So you don't need to download the PNGs. I just put them there so you can click on it. This is the one you download, the one that says output of, yellow diagonal output, and the input file, because those are the PNM files that we can difference with. And so that's what it's trying to difference with there. And then if you get the final one correct, then it will actually say matches the solution, looks like you are ready to submit. So that's the goal. But there's 4 functions here, and you'd start by implementing read image, and then write image, and then you'd see how they compare. And then once that works, then you'd implement yellow diagonal, and you see I've got some hints in here for you, and left right combine, and I have even more hints for you. And I want to bring your attention to, I have this function called get pixel index, and it takes a width, a height, a row, and a column. By the way, I think in my example I had column and row switch, so it looks like the one I have posted says row and column. And so it does this calculation for you, and it also does some error checking to make sure that you're not asking for rows and columns that aren't valid. So, so I think that's it. I hope this video is useful for doing the project. Again, I encourage you to start this weekend. I hope to see folks at office hours on Monday. On Tuesday, I really hope everyone started on the project and we can have a good session after lecture where I can answer questions. I think if you get started early and you get support, this project will be okay. If you wait and do it on your own, I think it's going to be a toughie. And in particular, where this can go wrong is indexing problems, going outside of arrays, crashes, and so on. And so that's something that the TAs and I really want to support you on. It's critical that you learn how to use GDB. and I'm hearing some reluctance about that. But this is the time to do it. It's something you'll need going forward in your careers. And so as you're running into those crashes, we really hope to see you in office hours, and we want to show you here's how you do it. And then hopefully you'll say, oh, I get it. GDB is actually good, and I want to use it. So that's it. Lecture 11 signing off. I'll see you all in class on